Alright, so today we are looking at our first topic for today is construction of manifolds through, I'm guessing this means, inverse images. And first off, we have a uniqueness principle. Theorem that X be a topological space A and B be full atlases on X, and alternatively XA or XB be the manifold whose underlying space is X, that is determined by A or B respectively, of course. Then the following are equivalent. XA, the manifold, is equivalent to the manifold of B. That is A is equal to B, of course. Secondly, for all manifolds Y, the morphisms from the manifold of XA to Y is equal to the set of morphisms from the manifold of B to Y. And third is the same, except this time Y serving as the domain of our morphisms rather than the codomain. And prove this is actually just a special case of the theorem we saw before, which stated that an object which represents a function is determined up to a unique isomorphism. Maybe that's not what we saw before, maybe that's a more general category, but anyways. The only non-trivial step in this proof is showing that 2 implies 1, because 1 implies 2 is automatic, and 2 and 3 are obviously going to be analogous to one another, so 2 implies 1. If we just set Y to be X alpha, we see that the identity on X mapping from XB to XA is a morphism, since it is equivalent, has an equivalent mapping from XA to XA as before. And similarly, its inverse is identity, but now we're being shown as mapping from XA to manifold XB is a morphism. A and B are therefore compatible atlases. And hence A equals B because they're full. Now we have two lemmas. We have some setup first, where we're going to let X and Y be manifolds, and the function f from X to Y being a morphism. on our first lemma. First off, suppose F is an immersion. Then, stating that G is a morphism from Z to X is equivalent to, first off, G being continuous, and secondly, the composition of G on F is a morphism from Z to Y. There's a second lemma. Both of these are immediate. Suppose F is a submersion. Then we'll first off, F is an open map. With f of x open in Y. Secondly, suppose f of x is equal to y. Then G being a morphism from Y to Z is equivalent to G on F being a morphism from X to Z. Alright, and that's our first of section here. Secondly, we have inverse image constructions. So, let X be a topological space, Y be a manifold, and F from X to Y be a continuous map. Now, brings us to our first theorem in this section. If there exists a manifold structure on X such that F is an immersion, this manifold structure is unique. And for proof, we saw from before that for all Z, the morphisms from Z to X is determined, the set of morphisms from Z to X is determined by the topological structure of X and the manifold structure of Y. So by previous theorem, the manifold structure is unique. So now we're going to pick an X and X. We say X comma F satisfies M at X if there exists an open neighborhood u of x in x, a chart C as v comma phi comma n of y, and a linear subspace e of k to the n such that, first off, f of u is in V and f is a homeomorphism. Of u onto its image. And secondly, phi of f of u is equal to the intersection of E and phi of V. Brings us to a theorem following our equivalent. First off, there exists a manifold structure on X such that F is an immersion. And secondly, the pair of X and F satisfies IM. Now we've already seen the proof of 1 to 2, so we're going to show 2 to 1. We choose an open cover UI over an indexing set of X such that for all I in I there exists a chart Ci being Vi, Phi, and I, and a linear subspace EI of k to the Ni satisfying well, first off, I'm going to use letters for this. F of U, each U of I is in V. Yeah. And F is a homeomorphism of UI onto F of UI. And B, Phi of F of UI is the intersection of EI and Phi of VI. Then there exists a manifold structure on U sub I such that F restricted to U sub I is an immersion. Also, on the intersection of UI and UJ, the manifold structures agree. By our previous theorem. Hence, there is a manifold structure on X compatible with the manifold structure on each UI. So F is an immersion with respect to this manifold structure. Now, so after that, suppose this is like we're done our theorem here. Now I'm just going to observe that suppose X and F satisfies IM. Then our previous theorem show there is a unique manifold structure on X such that F is an immersion. We call this, I'm just going to write it as part of the sentence, called the inverse image structure on X relative to F or just called the induced structure on X. And we can sometimes, if we want to be explicit, we can write this as X sub F. Now let's look at how you would actually use this kind of things. First off, let's look at submanifolds. Suppose X is a subspace of Y with the induced topology. And let dotless I from X to Y be the inclusion map. If X comma dotless I satisfies IM, we say that X is a submanifold of Y, giving X as locally closed in Y. Now we're going to let X, pick an element X from X. Say X is locally a submanifold of Y at X at X if the following equivalent conditions are satisfied. First off, we have that X with the inclusion map satisfies our condition IM at at X. Secondly, we can find an open neighborhood U of X and Y such that U sub X is a submanifold of U. And thirdly, there is a coordinate system x1 through xn at X and an integer p at most n such that X is given by coordinates x1 through xp being 0 in a neighborhood of X. Our second application is pretty short, on local homeomorphisms. So, when F is a local homeomorphism, X comma F satisfies our condition making the morphism F from X with this F structure to Y and atal. I guess atal is more of an adjective, but whatever. Our third application is inverse images of points. So we're going to let X and Y be manifolds. F from X to Y be a morphism. And B be an element of Y. Set X of B to be the inverse image under F of B. And we're going to pick an element from the inverse image of B. And we're going to study X, B, and X in a neighborhood of A. With a theorem. See that the inverse image of B is locally a submanifold of X at A if one of the following conditions is satisfied. First off, F is a subimmersion in a neighborhood of A. Secondly, there exists a submanifold W of X such that I'm going to use capital Roman numerals here now because I don't know what else to do. First off, W is contained within the inverse image of B. And secondly, the tangent space at A of W is equal to the kernel of the tangent space at F, sending the tangent space at X to the tangent space in B at B. I called things wrong there, but you get what I was saying. And the third condition is biphile, which states there exists a manifold Z, a point C in Z, and a morphism G from Z to X such that, well, first off, for all Z in Z, f of G of Z is just RB. Secondly, G of C is A. Thirdly, the sequence from TC of Z by TC of G to TA of X through TA of F to TB of Y is an exact sequence. And we see here in each case TA of XB is the kernel TAF from TAX to TBY as we saw before. And proof. First, it's by definition. Second is we will show there exists an open neighborhood of A being 0 in K to the M. No. Open neighborhood U of A and X. I write the wrong line, such that the intersection of U with XB is the intersection of U with W. And so first off, we can assume X is an open neighborhood of A being 0 in K to the M, and that X is W times V. Define function f from X to W times Y by the formula where f of W and V, well, we're essentially acting on V by f of W. So f is an immersion at 0. So once again, by shrinking X, we saw something like this before. X, we can assume F to be injective. Then we have that X of B is contained within the inverse image under capital F of W times B which is W times 0, which is isomorphic to just W. Okay, in case number 3, that's not what I wanted to do. Sorry, 1 second. And in our third case, we will show exists open neighborhoods W of C in Z and U of A in X, a decomposition of W into W1 and W2, and a morphism phi from W1 to X such that first off, phi is an isomorphism of W1 into a submanifold phi W1 of X be G factors as the map from W1 times W2 projection onto 1, so that gives you W1 by phi into X. And thirdly, finally, the intersection of U and the inverse image of B is G of W. So that G is a subimmersion at C. And once again, this theorem is local. So by locality, assume Z is an open neighborhood of C being 0 in K to the P, and that Z can be written as W1 times W3 G's. Okay. W1 times W3, where T to the W1 G is an isomorphism at 0, and that TW3 of G is 0 at 0. Let phi be the restriction of G to W1. And phi is an isomorphism at 0. So by shrinking W1, have phi be isomorphism of W1 onto a submanifold of X. Then 1 and 3, parts 1 and 3, phi W1 satisfies the hypothesis of part 2. So we can find an open neighborhood u of a and x such that the intersection of u and the preimage of b is equal to the intersection of u and phi of w1. So there is an open neighborhood w of 0 in w1 times w3 such that g of w is u intersected with xb. Then g is from w to phi at w1 is a submersion at 0. So by shrinking w and w1, we can find a product decomposition w1 times w2, so that for small u, for shrinking u, conditions are satisfied. And we're done with that theorem. So how long has it been, and how long is the next section? So it's been 1, 2, 3 pages. It'll be one more. I think I gotta do it. Alright, and we'll look at one more application today, and then we'll do the others tomorrow, and then carry on. So our last application for today is, should capitalize it, transversal submanifolds. So our setup, let X be a manifold with submanifolds y1 and y2, and we're going to pick X in their intersection, which I guess we're assuming to be non-empty. Then we have a theorem. We'll call an equivalent. First off, tangent space at x of x decomposes into the tangent, sum of the tangent spaces at x of y1 plus the tangent space at x of y2. Secondly, there exists a chart C of u phi n at x such that, well, what do we need our conditions? We need phi of u to be v1 times v2 times w. We need phi of u intersected with y1 to be v1 times 0 times w. And we need phi of u intersected with y2 to be 0 times v2 times w. Thirdly, find a coordinate system x1 through xn at x, and integers p and q at least 0, with their sum being at most n, such that, first off, y1 is given by the first p coordinates of x being 0 in a neighborhood of x, and likewise y2 given by x p plus 1 through x to the p plus q being 0 in a neighborhood of x. So 2 and 3 are equivalent pretty directly, and 2 obviously implies 1. So we just need to show that 1 implies one of the others. The easier way is to show that it implies 3. Since our y1 and y2 are submanifolds of x, we can find submersions. Say f1 from x to kp and f2 from x to kq, such that yi is the fi inverse of 0. Let x1 through xp and xp plus 1 through xp plus q be the components of f1 and f2. Then we need the map. By one of our assumptions, the map f1 with f2 sending x into xp and xq times xq is a submersion at x. So x1 through xp plus q is part of a coordinate system x1 through xn at x, which is what we wanted. And our proof is done. If we have such y1 and y2, we say that y1 and y2 are transversal at x. There is an immediate corollary from this too. Where suppose y1 and y2 are transversal at x, then First off, y1 and y2 are transversal in a neighborhood of x. Their intersection is locally a submanifold of x at x. And third, the x-tangent space of their intersection is the intersection of their tangent spaces. And with that, we will call it here for an episode. There's still a couple more we gotta go through, but we've reached a session's length here, so hopefully you'll join me next time to see the rest of them. Thanks for watching.